Okay, we're back and we're doing some rotations, and this is a little more advanced. This is the moment of inertia of objects, which by itself is something that we should know when it comes to rotations. It's one of the essentials. It's new specifically for rotations. It talks about the distribution of mass around an axis of rotation. Basically, the bigger this number is, the more resistance, the more inertia you have that resists a change in rotational motion. Okay, just like mass is a resistance to change in linear motion. So this is the quantity represented by a capital I that replaces mass, where we're used to seeing it from linear dynamics. Now specifically, what we're going to try to do with this particular video is take a look at some special cases. Now I already have one that introduces the so-called parallel axis theorem. And this is a theorem that's kind of a shortcut if you want to find the moment of inertia for an object which is spinning around an axis that is not the center of mass of the object. And the gist of it is that the moment of inertia in a case like that would be the normal moment of inertia when the axis is the center of mass, but then plus the mass of the object times the distance squared from the center of mass to the new axis of rotation. Okay, it's just this new little quantity that you add on to figure out the new moment of inertia. Okay, so there's a separate video just to introduce that concept. What we're going to do is kind of the next level of complexity or difficulty. And these show up on things like the physics Olympiad because it is a little more advanced. So for example, if you have like a disk or some object that is rotating, when it's just the normal symmetric solid object, okay, that's one thing. But what if you were to remove a chunk of the object? Okay, so for instance, if we have a disk which is going to rotate about its center, okay, so a pretty standard normal sort of rotation, but let's say down at the bottom I drill out a hole of radius small r. Okay, and then this whole thing, okay, the object minus the hole is going to start rotating around the axis of rotation at the center. Okay, how would you do this? Okay, well, first we know that the moment of inertia for a disk, okay, just a normal solid disk, is 1/2 mr squared. What's new and what's the key ideas for this particular video is the total moment of inertia for the new case with the hole drilled in it is simply the moment of inertia of the disk minus the moment of inertia of the hole. Okay, inertia is just a scalar quantity, so we can just subtract. These are just numbers, and we can just subtract the missing piece. But the trick is how do you find the moment of inertia of the hole? What does that mean? Okay, well, because the hole itself is also a disk, okay, we can think about the moment of inertia of the hole as the missing moment of inertia of a normal disk of that size. Okay, so let me start writing this out. Okay, so we're going to have what it would have been. Okay, so we have 1/2 times the mass of that missing piece times little r squared. Okay, but now notice that the center of the hole is some distance away from the axis of rotation. So this is relevant for the parallel axis theorem. Okay, this 1/2 mr squared for the hole, that represents just a normal disk. Okay, but then because the axis rotation for the hole is not its center of mass, we have to add in the mass of the hole times d squared. Now from our picture, d is the radius of the whole disk minus the radius of the hole. Okay, so we've got that. But now, how do you find, what's the mass of the whole? I mean, what's the missing mass? Well, what I'm going to think about this is I'm going to take the mass of the total disk, and then, this is just the whole is just some fraction of the total mass that is missing. And what fraction can we use? Well, this is where the distribution of mass comes in handy, okay, that concept. The distribution of mass is spread throughout the area of the disk as we look at it. Okay, so I'm going to say that it's the ratio of the area of the whole, pi little r squared, over the entire cross-sectional area of the entire disk, pi big R squared. Okay? That is the fraction of the total mass of the disk that's missing. And that's going to be multiplied by little r squared for the first term. And then we're going to have the mass of the whole, which is the same quantity, times little d squared. Okay? Well, in the end, we can simplify this down a little bit and say, okay, well, this is going to be 1/2 times the total mass. On top we have a little r to the 4th over big R squared. Okay, the pi's drop out. Plus the mass times little r squared. Now d squared is going to be the quantity total radius minus the missing radius squared all over big R squared. That's the moment of inertia of the whole using the parallel axis theorem. Okay, so the end result is we have to take this whole quantity. I'm not going to simplify it. That's going to be a waste of time, but we're going to have the moment of inertia of the disk. Okay, so I'm going to substitute in just the normal moment of inertia, 1/2 total mass times total radius squared, minus this new expression that we have for the whole. Okay, and that final expression would be the craziness that is the moment of inertia of this particular object with the hole in it. Okay, so let me take one other example. We're going to modify what we just did. Okay, we'll have the same system. We have the same disk with the same hole, but now instead of the axis rotation being at the center of the original disk, let's move it and put it at the edge. Okay, at the top here in this picture. So you're going to have this entire system. Okay, the center of the disk is going to be revolving around the axis of rotation up here, up at the top. Okay, what's this going to look like? Well, here we're going to have to use the parallax theorem on both the disk itself as well as the whole. The key idea is still the same. We can subtract. If we can find these two inertias, we can subtract them to get the inertia of the whole system. Okay, so let's just work on this. Let me first find out the inertia of the disk. And we'll just assume that there is no hole. If we just had to do this from scratch, we can just use the parallax theorem and say, okay, well, the moment of inertia of a disk at the center of mass is just the normal 1/2 m big R squared. Okay. Then the parallax theorem says we have to take the mass of the disk and multiply it by the distance from the center of mass, which is dead center, to the axis of rotation, which is at the edge of the disk. Well, that distance is just the radius of the disk. Okay, so this is going to give us 3/2 mass times the full radius squared. Okay, what about the whole? Well, we're going to do a similar thing to what we did above. We're going to have to find out just the normal moment of inertia about its center. So we'll have the mass of the whole times little r squared. But then we have to add to that the mass of the whole times the distance from its center of mass to the axis of rotation, which is just little r. okay, when it's at the edge there. So this is going to be 3/2 whatever the mass of the hole is times the little r squared. Well, let's do our trick from above. What's the mass of the hole? Well, that's going to be the total mass of the disk multiplied by the fraction of that area, pi little r squared over pi big R squared, okay, times little r squared. Okay, so this is going to simplify down to 3/2 total mass times little r to the 4th power over big R squared. Okay, so if we include these now in our formula here, we can get the moment of inertia of the system. So we're going to have the 3/2 m big R squared minus 3/2 m r to the 4th over big R squared. And this one we can go ahead and simplify just a little bit to get some final expression. Okay, that's supposed to be r to the 4th power up there. Okay, so again, it's the parallax theorem, and we're using it to find out what the inertia of these holes are that are in the objects. It's a matter of trying to find out what percentage of your total mass is missing, and then just subtracting the two inertias, the normal inertia for the disk minus the missing piece. Okay, so in both cases, they're kind of similar. It's the same idea. And these are probably the most sophisticated types of moment of inertia type problems that you can get. Okay, so I hope this helps, and until next time, we'll see you later.